Okay, Rose, let's tackle lesson 7.5, our last lesson before we focus on course review. In 7.5, we looked at the present value of simple ordinary annuities. And the idea of using an annuity, an ordinary annuity, should have made a little bit more sense in these questions where we are either making a deposit now and then taking out money a little bit later, or we are buying something now and then making payments later. We'll see how that makes sense on our timeline, which is how we're going to begin. Let's start with the development of a specific formula and see how we could avoid having to memorize another formula. So we are going to find an expression for the present value of n payments of R dollars at I% per compounding period made at the end of each period. Okay. Let's just shift this over a little bit. Like that. Okay, so here's our timeline. We have payment number 1, payment number 2, squiggle, squiggle, payment number n minus 1. You might need payment number n minus 2 over there. Sorry, there's a bit of delay on the video, so the voice might not line up. We are making these payments at the end of each period, like that. And we want to figure out either maybe how much do we need to deposit now to make those payments, or if we borrow this money now, how much do we have to pay at the end of every period to have it paid off or exhausted, which is one of the graphs that we'll deal with at the end here. So like we did in 7.2 or 3, I think, with present value of lump sums, we're going to track these values backwards in time. Now at I% per compounding interest, we're going to be discounting by a factor of 1 plus I. We use the expression 1 plus I to the exponent negative 1. When we were doing future values, we were going right or forwards in time. When we're doing present values, we're going left or backwards in time here. This should remind you, let's wait till we get to the last one right here, but it should remind you of tracking present values of lump sums. That's how we're approaching this annuity. We're going to treat it as n lump sums, and then we add them all together. That's way easier than doing all the calculations on top of each other. That's going to be discounted backwards 2 times, ... I think we can survive with actually just this last payment here. It's going to have the most time to grow, so its present value will have to be the smallest. We sometimes use an analogy here of a Christmas tree farm or a holiday tree farm, where we'd like to have a tree of height R at the end of every single one of these years. The same height every single year, right? Maybe, I don't know, 6 feet tall. 1.9 meters tall. Well, we would have to plant a pretty tall tree right now if we need to have a tree be 1.9 meters tall next year. But like 10 years from now, we could just plant a tiny little tree because it would have time to grow. Okay. So yeah, what we're doing here, let me just slide up for a little, or you can find some space over here. You may recall we said that the amount of a lump sum is its principal multiplied by 1 plus I to the exponent n, or we called this future value and this present value. So if we isolated for present value, we could have done future value divided by 1 plus I to the exponent n. But then we just pulled some grade 11 unit 3 Kung Fu and used a negative exponent instead and tracked it backwards in time. Okay. So here are the future values of all of our payments present value of all of our payments, and the present value of the annuity as a whole is going to be the sum of this series right here. Now, we're going to do another little trick here, a little bit different than before. In all of our future value situations, we were using the last payment as the first term. It might have confused a few students, but it made sense when we looked at the exponents. Our exponents here might cause a bit of a concern because they're negative, and if we read it in this direction, they're actually going down. So once again, I don't want my first payment's value, present or future, to be my first term. I'm going to set that to be my first term so that when I read in this direction, my exponents are going up. If we make that our first term, then our common ratio is still going to be 1 plus I. If we were to make this our first term, which is one approach that our textbook uses, then our common ratio would have to be 1 plus I to the exponent -1. And it makes our formula a little bit trickier. Okay. I'm going to illustrate that just in maybe in the margins of our timeline here. Imagine I gave you a geometric series where we had S of n being 1 plus 1/3 plus 1/9 plus 1/27. If we treated our first term as 1, then our common ratio would be 1/3. I'm dividing by 3 or multiplying by 1/3 each time. But we are masters of the commutative property of addition. We should understand that it doesn't matter what order we add in. This is kind of what Gauss did, I suppose. If we just change the order around, we're in charge of what we want the first term to be. If we make our first term 1/27, then it makes my first term a little bit more complicated, but it makes my common ratio a lot simpler. Now my common ratio is 3. We just kind of like growing sequences better than decreasing sequences. Okay, so one last time into our, or second last time, into our sum of a geometric series formula. The only formula we really need to memorize to deal with any kind of annuity here. We substitute in that S of n is going to be our present value. We're going to treat our first term as r times 1 plus I to the exponent -n. Maybe a big set of square brackets. Our lowercase r, our common ratio of this sequence, is going to be 1 plus I. You could try doing this term divided by that term. You'd keep your base and subtract your exponents, and you'd get the exponent of 1. Sorry, this term divided by that term. Future divided by previous. We're going to need, that's going to be to the exponent n, because there's n terms. We subtract 1. And then once again in our denominator, the 1 plus I minus 1 simplifies down to I. And there you go. Okay. Now, if you were to look at your future value formula side by side here, which I'm going to do, or on top of each other here, if your future value was just r, we had the first term being r, our common ratio was 1 plus I, there were n terms, they look very, very similar. In fact, you might realize that the only thing that the present value function or operation has that the future value doesn't is this discount going back and periods. So if you're really paying attention here, you might notice that the future value of a simple ordinary annuity is going to be, your present value of a simple ordinary annuity is going to be your future value times 1 plus I to the exponent -n. So I've seen situations where students in a question accidentally calculate the future value. It can have some interpretation impacts as well. But let's say, oh no, we accidentally calculated the future value instead. Here's our future value. You don't actually need to erase everything and start over. To get your present value, you just take this and discount it backwards. Your present value is going to be your future value. Instead of counting all of these backwards, you could count all of these back by a factor of 1 plus I back n periods. It's another one of those cases which happens an awful lot in our course, where if you understand it, it makes a ton of sense. Versus if you try to memorize it, we have a lot to try to memorize, where it'd be so easy to mix it all up and say, oh, I can't remember the formula. There's one formula that we've already memorized, and that is the sum of the geometric series. One formula. Okay. Let's try this out with a numeric example, and then in the numeric example, I'm going to make this numeric example relatively small, because I want to actually show you what happens with these values in a loan type situation or an investment type situation. I remember really enjoying this as a student. So let's say Ivan wants to make payments, or wants, like he wants to receive, wants payments of $500 at the end of every month. Off for 4 months. Let's figure out how much must he invest now. At 9% per annum, compounded monthly. We could try memorizing the formula that we just developed, or we could draw a timeline and figure it out as a series. Let's do that. So there's a couple of things that could be happening here. Maybe Ivan has paid for something and financed the price, and now he needs to make payments. That's not what it looks like in the wording, though. It sounds like maybe Ivan anticipates that he's going to have to make payments of $500 at the end of every month for the next 4 months. Maybe he is in a college program and his rent of $500 is due every month, and he doesn't want to worry about it. He wants to have a lump sum to just sort of sit on here, and he's found an investment. And he wants to invest all of that money right now so that he can take out $500 and then have money for his rent, so that he doesn't need to worry about it there. Right. I have seen students struggle on questions like this when they are trying to memorize some of the simplest formulas about like relating time, the number of payments, and our frequency. I've seen students say, oh, I need to figure out N, I need to do T times F. So they struggle to figure out what T is. Oh no, what's in 4 months, so I need to convert that to years. That's like 4/12 of a year, 1/3 of a year, and then I multiply by 4. Those students aren't realizing that, like on a timeline, you can see we're making monthly payments, 2, 3, 4. There's 4 monthly payments, so the number of payments is 4. Don't make the question harder for yourself by trying to memorize stuff. Okay. All right. This payment rate here is going to have the least amount of time to grow. Its present value is going to be 500. 1 plus 0.09 divided by, we are compounding monthly. We're compounding paying monthly, which means that it's a, let's identify that again, compounded monthly, end of every month. This makes it a simple annuity. The fact that we are making the payments at the end of each month, or taking out $500 at the end of each month, makes this an ordinary annuity. Again, unless otherwise stated, every annuity in your textbook is a simple ordinary annuity. Right, sorry, this is tracked backwards, 1 period. This one's going to be tracked backwards, 2 periods. In this case, 0.09 divided by 12, I'm pretty sure it terminates, but that's not always the case. So, and this is a weird case where it might not take much longer to write out actually all of these payments here. That's going back 3. This one right here is going back 4. Now, Ivan shouldn't have to deposit $2,000 right now. If he put it in under his mattress and then just took $500 out of his mattress at the end of every month, then yes, he would need $2,000, because that money's not going to grow anything other than mold underneath his mattress. Because of interest, this one right here, he needs to have like nearly $500 to make that payment. This one right here has the longest amount to grow, so its present value should be the smallest. His present value is going to be the sum of that series. And again, if we choose this to be a, if that's our first term, then our common ratio is going to be 1 plus 0.09 to the exponent 12. It'll reduce the number of negative exponents that we have in its formula. It's worth it. Let's do the calculations here then. S sub n is going to be a times r to the exponent n minus 1 all over r minus 1. In this case, we're solving for the present value. Let's treat this as our first term. The power with the smallest exponent we'll treat as our first term. 500, 1 plus 0.09 divided by 12 to the exponent negative 4. Then we have the common ratio of 1 plus I, 1 plus 0.09 divided by 12 to the exponent, the number of terms that I have, that's positive 4, minus 1 because of the formula, all over 0.09 divided by 12. Okay. This might not be the first time that I've recorded this video. First time the microphone might have been off. And I remember having trouble with this operation. So be careful with it. There's plenty of opportunities to make mistakes. I am going to try typing it all in one go. I'm not sure. Well, I think maybe the screen is more valuable to see than my button presses. I'm going to try it out. From left to right. 500 bracket 1 plus 0.09 divided by 12 to the exponent negative 4. There's a bit of screen glare. Bracket, bracket, 1 plus 0.09 divided by 12, bracket, exponent 4, minus 1, bracket, divided by, bracket, 0.09 divided by 12. Okay, now, we're expecting a number less than 2,000 because it should have a chance to grow, but this is also just 4 months. We shouldn't expect a number like that much smaller than 2,000. Like, you shouldn't just invest, I don't know, $400 and then magically have $500 each time. So yeah, when I type enter, I should be able to predict whether this is reasonable or not, especially with a small time frame like this. And yeah, this is a little disappointing that he's actually only getting like, what, $37, $36.95 of interest. But Ivan doesn't have a lot of time, so anyway. That is the correct answer, I believe. The present value of this would be about $1,963.06. So he must deposit this much. Huh. It's not too bad. If you use, there's other versions of this formula out here. If you use the first payment as your first term, then this is going to have a negative exponent in it. You could then like distribute that through. Then there'd be like a 1 plus this minus to the exponent, negative 1 minus 1 in your denominator. It is a lot messier. I'm not sure you really want to think about doing the future value first and then discounting, because this is what I want to show you. Technically, in the future, Ivan is going to have $0. Is he's taking the money out here. This is called exhausting. There's not many questions in the homework or homework opportunities or test or quiz opportunities to do this, but let's do a graph to see what happens here. And we're going to be doing manual calculations, which is also unlike us. There's only 4 of them, or maybe 8 kind of thing. So here is the amount in Ivan's account in dollars. And this is going to be time in months right here. Okay. So let me show you this in a forwards direction here. Let's see. Let's have that be 1,000. Have that be about $2,000. Almost to scale right here. So Ivan deposits $1,963.06. Right? And he sits on that money for a month, and it is going to grow. It's going to grow exponentially because it's compounding here. At the end of 1 month right here, this is going to grow $1,963.06. It's going to grow at a rate of, or by a factor of 1 plus 0.09 divided by 12 to the exponent 1. Growing to $1,977.78. But then it's the end of the month. His rent is due. He pays $500 rent. So there's a drop immediately of $500. I subtract $500 from that. And right now Ivan has $1,477.78. Okay. And then that sits there for a month and it grows. Excuse my scale. It doesn't grow quite as much as this did because now there's a lower principal. But it's going to grow at a rate of 1 plus 0.09 divided by 12. Or by a factor of, sorry. And now it's worth $1,488.86. And that's at the end of 2 months. So he keeps on taking money out of this, but it has a chance to grow as well. So it diminishes a little bit slower. Let's take off $500. I really shouldn't need a calculator to do that, but I want the number in my calculator anyways. And now we're down here at $988.87-ish. Right. Next month, or during this next month, that'll have a chance to grow at 1 plus 0.09 divided by 12. Now it's worth $996.28. And we make our third payment of $500. We subtract $500 from that. And now Ivan's down here at $496.28. So this is what I always thought was cool when I saw this as a student. Right? This money right here is going to grow. And this is the worst way to try to do this question, to sort of walk it backwards and say, okay, so I need to have how much money should this grow to in interest? Shouldn't it be exactly $500 so that he can pay off that $500 and get that there? So this is not how you want to do the question. You don't want to say, okay, at the end of the 4th month, you should have 0. So you add 500, you discount that, you add 500, you discount that, you add 500. We want to treat it as a series, but just to convince you that it actually works, here is our current present value. We let that grow by a factor of 1 plus 0.09 divided by 12. And we get, rounded off, about $500. We make that last payment of $500, and then the fund is what we call exhausted. Right? And I always thought it was really cool that these calculations up here, like just doing that right there, figures out exactly how much I would need to deposit so that this sort of step pattern happens, so that it grows, I subtract, it grows, I subtract, it grows, I subtract, it grows exactly to 500, round it off, I subtract, and then it's exhausted. And imagine this in like one of our retirement questions where we make like 312 payments. When you sit back and look at it, it's pretty cool, the type of math that we're able to do by the end of this course. That is assuming, of course, that we have been practicing. And don't learn mathematics by watching, even by watching YouTube videos. So, make sure that you try it out. Take care, Rose.